Hello everyone, my name is Alex Laval. My co-authors are Bashak Sakchuk and Steve Laval from the University of Oulu, and the title of our paper is Bang Bang Boosting of RRTs. First, let's consider the kinodynamic planning problem. We are given a robot with an n-dimensional configuration space and fixed obstacles. Initial and goal states are also given, and the task is to compute a control that takes the system from the initial to the goal while avoiding obstacles. This problem was introduced by Donald et al. In 1993. The RRT was introduced in 1999 as a sampling-based approach to higher dimensional kinodynamic planning. And it is well known that the RRT performance depends heavily on having a good steering method, and our paper follows in this direction. First, consider a double integrator model. The system is q double dot equals a, in which a is an acceleration input that has unit magnitude or less. In the phase plane, constant accelerations produce parabolas. Consider steering from an initial state, xi, to a goal state, xg, in minimum time. From Pontryagin's maximum principle and some analysis of these parabolas, the optimal control corresponds to two constant extremal accelerations. For this example, it is hard acceleration followed by hard deceleration at x switch. For higher dimensional configuration spaces, we have one double integrator for every degree of freedom. We do time optimal steering for each configuration coordinate, but there is a hard problem. All double integrators must arrive in their goals at the same time. Due to momentum, they cannot wait without drifting. This is the time-optimal bang-bang control for a problem that maintains non-zero velocity. In other words, we don't touch the q dot equals 0 line. The accelerations can be lowered in magnitude to cause some delay. This allows even more delay, and this is the limit of how much delay can be done. It is hard deceleration followed by hard acceleration. If the curve goes too low, then no acceleration can be applied to get to the goal. The best we can do is wait for an extra interval of time, as the trajectory follows the extra football shape shown here. We call this the gap interval. Note that once the q dot equals 0 line is crossed, we can wait any amount more as needed. We then developed a sweep line algorithm to determine the minimum time in which all double integrators are able to arrive at the goal. It takes n log n time. The method works by sorting all optimal times and gap interval endpoints for each double integrator. Then it sweeps from lowest to highest time while updating the number of double integrators that have solutions for each critical time. The method terminates when the count reaches n. We end up with a fast, exact time-optimal steering method. This is used for both the local planning and the RRT metric. We applied it to balanced bidirectional RRTs, but could in principle be applied to any sampling-based methods. We also have an extension to non-double integrators. Here is a simple computed example that compares the original RRT to our new approach. The exploration is much more efficient, and it is about 1,500 times faster. There are also far fewer nodes, less collision checks, and short solution paths. These numbers were averaged over 1,000 trials. We can also use our steering method for optimization by picking pairs of points at random along the trajectory, and attempting to replace each segment by a time-optimal segment. We iterate until no significant improvements can be made. Here are some animated results. The first example is a 2D hovercraft in a field of small obstacles. The black and red trees are the two RRTs. The green trajectory is the solution it finds, and the purple trajectory is the result after shortcutting. And finally, we show a problem of trajectory optimization for a planar linkage with 1,000 degrees of freedom. The initial trajectory is shown first, followed by the optimized trajectory. This paper also includes experiments for a non-double integrator. We consider a vehicle that moves like a pendulum in one direction and a hovercraft in the other. The new planner consistently solves such problems, being a few times slower than the original level ground case. To conclude, we developed a new steering method for kinodynamic planning. It was applied to RRTs and shortcutting-based optimization. The hardest part was the time gap interval problem. We developed an efficient solution to that, which runs an n log n time for n double integrators. The paper contains proofs, including time optimality of the steering method. The results are up to 1,500 times faster than the original RRT. Shortcutting was applied successfully up to 2,000 dimensions. We have some results for non-double integrators, but more work remains to be done to consider other dynamical systems. We also hope to try the method with an asymptotically optimal planner, such as RRT star. Thank you very much.